Good afternoon, everybody. We've heard a little bit about the RevB project, and we've had a couple of talks about some of the work that's been done at the kind of higher level in terms of BMS modeling and some of the mechanistic modeling that Monica and Sang have been doing. I'm going to talk a little bit about what we've been doing, kind of looking down a scale a little bit, trying to understand how reaction processes and even species interactions might be having an effect on the behavior of a lithium-sulfur cell. Just to give you a quick overview of the talk, I'm going to quickly cover what's currently done in terms of or the general approach that's taken towards describing lithium-sulfur models and kind of how the approach that we're using differs. I'm going to take a look at how this method actually works before looking at two different kind of applications of the model. The first being looking at reaction mechanisms, or rather how reaction processes can interact. And then the second being kind of at a microscopic scale, what might be happening in terms of species interactions and how that's affecting the system behavior. So typically we have this, for a lithium-sulfur cell, we have a porous cathode structure. To model this, usually it's completely homogenized, so you average out the porous properties of the cell, and you end up with an average pore, an electronically conductive phase, and you can have current flow through both of these phases, and you can model charge transfer between them according to electrochemical reactions. The average pore can be affected by precipitation reactions, so kind of with this we can build up reaction mechanisms which approximate what might be happening in a lithium-sulfur cell. There's a few problems with this model kind of at one level in terms of it's quite difficult to get the model to charge. It's also quite sensitive to its initial conditions, but at a more fundamental level, there's the assumption of dilute solution theory and electroneutrality, both of which are unlikely to apply. So we've heard the electrolyte's been described as a soup this morning. We've got all these different species in the electrolyte. It's a relatively high concentration. They've all got different sizes because you've got large polysulfide species and small polysulfide species. And how these interact might be affecting the performance. So what we wanted to do instead was to try and build a slightly better model for the electrolyte, incorporating species interactions, and also because electroneutrality is, or rather the system is most non-electroneutral at the interface between the electrode and the electrolyte in the double layer that forms at the surface. We kind of wanted to introduce the actual interface to see what might be happening there. Within this model, we can still build reaction mechanisms. They look a little bit more complicated, but because we've got an actual interface between the electrode and the electrolyte, it makes sense to separate out the electrochemical steps from the chemical steps. So the electrochemical steps have to happen at the surface, and the chemical steps can happen anywhere in the electrolyte. And we can still couple in a precipitation and dissolution reactions. I should say that this reaction mechanism is just kind of an example. It's not necessarily what we think happens, but it just shows how we can get from sulfur down to lithium sulfide. Just to give an idea of the general structure of the model, the electrolyte is kind of the dominant part of the model. So you can describe species fluxes and the electric fields within the electrolyte. The particular interaction that I've included is the excluded volume interaction. So this is the fact that two particles can't occupy the same volume of space. It's a relatively simple hard sphere model, just to see what effect that has. We could also describe chemical reactions in the electrolyte, and then at the surfaces, these are all coupled to electrochemical reactions, which can change surface charge density, and this is kind of coupled to the current. And then also the chemical reactions happening at the electrodes, which can be coupled through to a precipitation model. It's a simple hemispherical growth model at this point. The model itself, it behaves slightly differently to the way you'd use a homogenized cell model, in that it's kind of like a real cell, in that there's no voltage on the electrodes until you've added an electrolyte, and all of the electrochemical reactions, which are initially out of equilibrium, take place. These provide charge to the electrodes, generating a voltage. So the first step of running this model is always to reach, to determine this initial equilibrium voltage. The I'm going to demonstrate this just with what we kind of take to be the first couple of steps of lithium-sulfur discharge. So this is the dissolution of a solid precipitate and its subsequent electrochemical reduction at what will become the cathode. And then at the anode side, kind of an electrodissolution reaction of the lithium ions. You have to assign reduction potentials to the reactions. I'll come back to what these mean in a minute. And yeah, so as I say, the first step is this initial equilibration phase. And what I'm just going to show here is kind of what this looks like for this very simple system. The larger plot on the right-hand side is just going to show the evolving cell potential and kind of the potential difference between the electrodes. And then the two smaller plots on the left-hand side show the actual potential within the electrolyte itself, within the first few nanometers of the electrode surfaces, so across the forming double layer. So what we see is that there's initially a very, very rapid growth in the cell voltage. This is all entirely contained at the anode surface. And it kind of levels out as the anode reaction reaches an equilibrium state. It's just because this reaction is so active, it happens very quickly. Slightly later, the lower potential cathode reaction contributes towards the cell potential as that electrode moves towards an equilibrium state. And overall, we end up with a total cell potential, which is about 3.2 volts. It's kind of just approximately what the voltage of a very freshly built lithium-sulfur cell would be before you started discharging it. The thing we can kind of see here is that the cell potentials are all entirely contained within the double layers, and that the reduction potentials that we define for the reactions correspond to the potential difference between the electrode and the electrolyte itself. So there's kind of some question of how you define reduction potentials, because you can't define the potential of the electrolyte really. And I'll come back to this shortly. There is one other thing that's of interest here. You can see if we zoom into the final part of the equilibration phase, which is there is a second step. This corresponds to the dissolution reaction. So the red line on the larger plot shows the radius of the species, the precipitate species. And towards the end of the equilibration phase, there's a drop in the radius indicating the species is dissolving. This corresponds to this increase in the cell potential, which is caused by the dissolved species altering the activities of the species in solution, which shifts the equilibrium point of the electrochemical reaction. So it's the first indication that we're seeing some coupling between the chemical and the electrochemical steps. And this affects the equilibrium stage. Obviously, with a model cell, we want to be able to charge and discharge it. We do this in the same way as a real cell. We apply a constant current to charge or discharge it between a voltage window. In this case, when we start the model running, we can see that the voltage drops, you reverse the current, and the voltage increases again. But probably the most interesting thing, or one of the two interesting things here, is that most of the voltage change all occurs at the cathode side. Again, the anode is so reactive in this particular system that there's very little really happening there. And you can see that the voltage on the cathode shrinks and grows. The other thing is that there's a change in the amount of precipitate on the surface. So we've very much coupled the chemical step to the electrochemical properties of the cell, such that on discharge you lose all of the solid phase, on charge you regain all the solid phase. Now, as I said, the definition of the reduction potentials is difficult, and as one of the questioners earlier pointed out, determining all of the parameters of this type of model is actually very difficult. We can't define rate constants or diffusion rates and all these sorts of things. So the way that we use this model is to try and build up simple reaction mechanisms and conduct parameter sweep across all of the possible parameters to look for trends in the voltage profile, which we think start to look like lithium-sulfur in this case. So one of the first things we've seen is just looking at a very simple reaction mechanism starting from a solid phase electrochemical step followed by a dissociation step. and a subsequent precipitation of that product by reacting with cations from the anode, we can generate voltage profiles which look kind of like this, where you have a voltage drop followed by slight recovery, a very flat voltage profile before it decreases to the voltage cutoff towards the end of discharge. And generally what we find from looking at reaction mechanisms like this is that it's almost essential to have the precipitation step at the end. The precipitation step acts as initially as a bottleneck, and then you can see about 1,000 seconds in this case that the radius of the species BC starts to increase at the same point at which the voltage enters its plateau region. This kind of indicates that the precipitation is affecting the voltage profile, and it kind of ties into what we see with homogenized models, whereby precipitation, or rather the onset of the end of this precipitation occurs at the beginning of the second plateau. And it's also something that ties into what's seen experimentally, whereby lithium sulfide formation appears to start at the transition point between the two plateaus. So it kind of indicates that we might be seeing, or rather we can use the model to explore how reaction mechanisms, reaction processes interact. Now, one of the things you can see, or rather you can't see, is that there's no high voltage plateau. So to generate a system with a high voltage plateau, what we tend to find is we need two electrochemical steps. So expanded, this is still a linear reaction chain, but we allow the first dissociation reaction to undergo a second electrochemical reaction, and then there's a further dissociation and precipitation step. So in this case, we see that we get a very clear two-step voltage profile, one at about 1.9 volts, one at about 1.5 volts. But what's kind of interesting here is that this isn't really because of the electrochemical reactions. It's because both of the reduction potentials we just said are equal, and it seems to be more related to the chemical process, the chemical step, this first dissociation reaction that seems to act as a bottleneck in this case, causing the difference in the voltage. This is kind of where we're at in terms of exploring the parameter space as far as understanding how reactions interact. So I'm going to move on to the second part. As I mentioned at the beginning, one of the other things we're looking at is species interactions might be affecting the behavior of the system. So to try and probe this, we take a very simple look at the cathode structure. So we assume that there's some agglomerate of carbon phase in the cathode structure, surrounded by an electrolyte, and that this carbon phase is crisscrossed with micropores. We then simplify this right down to a single micropore connecting two electrolyte baths. And all we're going to do is apply a voltage between the carbon phase and the electrolyte phase. And what we're interested in is what happens to the concentration profiles within the pore. So to do this, we define an electrolyte. It's got 6 species in it, 2 groups of 3 of 2 different sizes, and then the charges as listed in the table. So there's one of each positive ion, a negative ion, and a neutral species for each ion size. And we apply a voltage, work out what the equilibrium run the model to equilibrium, and then look at how the concentration profile changes across the red line. So we start this running. Now we've applied a positive potential to the surface, so what we'd expect is negative ions to be drawn into the pore and positive ions to be expelled from it. In terms of the positive ions, which is the red lines, you can see that this is indeed the case. The concentrations get suppressed near the walls of the pore, and that as you increase the voltage, the region in which it's suppressed kind of gets pushed towards the center. All of these species have to be leaving the pore at the ends. So we're losing the cations from the system. Now where the same thing happens with the neutral species. This is something which you'd never see in a dilute solution theory model, or and which homogenization kind of flattens out of any model, which is that species interactions lead to the loss of neutral species which don't interact electrochemically with electrostatically with the surface, but they do interact through the volume interaction terms. The other kind of even more interesting thing possibly is that as you increase the voltage, the smaller of the two species very much dominates the concentration of this micropore, and to the extent that the larger species is also excluded, even though it's negatively charged. Now, the extent of the exclusion kind of depends on a range of factors. It depends on the voltage that you applied, the size of the pore, the size difference between the species. As I said, you've got electrolyte solution, which has some very large high-order polysulfide species, as well as some much smaller low-order polysulfide species, which potentially has some consequences in terms of when you start thinking about the mechanisms. So if you've got regions with, or rather if you've got a cathode which has pore size variation, it seems likely that you're going to end up with a case that you've got a variation in distributions of high order and low order polysulfide species. This means that when you try and draw a current from the cell, it's entirely possible that you have different parts of whatever your reaction mechanism is happening in different parts of the porous structure. The other implication relates to precipitation. So we saw that the cations get pushed out from the pore, which means they're likely to be hanging around at the ends of the pore. And then you've got all your low-order polysulfide species inside it. So depending on the extent to which species are excluded, it's possible that when your precipitate species forms, rather than kind of nicely coating the inside of the micropore, you end up with kind of plugs forming on either end of the pore. And the difference between these two processes is likely to lead to kind of mechanistic differences in how the pore structure affects the system. Okay, so just to quickly summarize, we've been working on a model where we've tried to include species interactions into the system and looking at how reaction processes might interact and how those species interactions might affect the system behavior. And these interactions potentially have a significant effect on the behavior of the cell. And just finally, I just want to, as well as co-authors from Imperial and OXIS Energy, just to quickly thank the other collaborators on the project and the rest of the R&D part at OXIS Energy. And thank you all for listening. And any questions?
Questions? That was not a plant at all.
So although I'm a co-author, so I probably shouldn't ask a question. So, I mean, this morning with Professor Wu from Taiwan was discussing the redox mediator theory. I mean, does this work lend more weight to that? If the only species that can get near the electrode are the small species, then the only way to reduce the large species is diffusion and chemical reaction.
Potentially, it might depend on what the variation in the pore sizes is. If you have a very high proportion of very small pores, then potentially that would affect the dissolution mechanism. If the pores are much larger, I'm not sure you could say from this model that would be the case. So possibly.
If we don't have any further questions, we do.
So you have shown that although you have two electrochemical reactions that have equilibrium around the same potential, you reach the two plateaus. And I think many people in the modeling community are taking those plateaus as a reference to extract the equilibrium potential.
Yeah.
So is that, I mean, what is the relevance of that with respect to like proper normal lithium-sulfur functioning?
It's more to, kind of the reason I included it is more to possibly to point out that you don't, we know so little about the lithium-sulfur cell, it's actually posing an even like more questions almost. Is the difference in the voltage profile because you have distinct voltage plateaus. There's kind of the question that you have so many, there must be quite a lot of electrochemical reactions taking place. Why do you not see more than 2 plateaus? And so it might actually be a different mechanism which is dominant, and then you don't see the other plateaus because it's hidden by a chemical step. So I'm not sure how it would relate to the standard approach.
You know, so then this shows that this would explain why in very different system, what you would expect to have very different electrochemical paths, you still have the same characteristics.
Quite possibly, yes. Yeah.
Okay, if you don't have any further questions, it's thank the speaker again. Thanks. Okay.